Imagine you are climbing a ladder you set up to reach the roof of your house. As you ascend, you feel a pit in your stomach as the ladder tips to the side and you begin to fall. You are about to be one of over 22,000 Americans who suffer ladder-related injuries every year. Many of these injuries are caused by ladders being set up on unstable surfaces, making them more likely to tip to the side and fall. I'm Johnny Rigonati.
I'm Andrew Omer.
I'm Andrew DecaCast.
And I'm Ashley Falk.
And we're here to bring you LegUp, a versatile and durable solution to ladders becoming unstable. Homeowners who use Type 2 and 3 extension ladders are at risk of injury due to falls while operating a ladder on uneven surfaces. An uneven surface can cause the ladder's feet not to make full contact with the ground, making it more likely to fall to the side.
The vast majority of interviewees reported that they often doubt the stability of their ladder. However, many of those same people also reported using unstable homemade solutions such as stacking bricks or cinder blocks or even using nothing at all. A few solutions to this problem already exist, but each have their own flaws. The lockjaw ladder grip attaches to the top of a ladder and cannot be used on a flush surface. The Werner Level Lock Ladder Leveler is only compatible with certain Werner brand ladders and has limited adjustability. And lastly, nobody wants to buy a whole new ladder to replace their function. Keeping these issues in mind, we created our criteria accordingly. The device must support up to a 250-pound load with a safety factor of 4, adjust up to 10.5 inches vertically, present no additional laceration or puncture hazards, and fit onto any Type 2 or 3 extension ladder within OSHA regulations. We considered many alternative mechanisms for a device, such as attaching to the ladder with elastic or ratcheting straps or clamps, as well as adjusting its height with a pin and leg or jack stand mechanism. Ultimately, we decided on our current iteration, attaching with thumb screws and adjusting its height with a sliding leg that locks in place with a cam.
To attach LegUp, all the user has to do is loosen the thumb screws on the exterior of the device, lay their ladder down on the ground flat with one leg sticking up, slide the device up the ladder leg until the ladder foot makes contact with the platform on the device. Once there, retighten the thumb screws and you should be ready to begin use. On screen now is how our device's locking mechanism functions. When in use, the reaction force of putting the device on the ladder on the ground with the device attached will put a vertical force on the leg. This vertical force will push upwards onto a yellow cam that will rotate until stopped by a blue stopper piece molded within the leg. At this point, the ladder leg will not change heights until the user dictates to do so. And that brings us to how to change the heights. When wanting to make the leg move downwards, adding more height to the leg to be able to close larger gaps in height, all the user has to do is simply pull down on the leg. This is due to that yellow cam now rotating downwards while still having a vertical force applied to it by the spring. And once you're at your desired height, stop pulling down and it will relock itself into place. And lastly, when wanting to make the leg move upwards to be able to close smaller gaps in height, all the user has to do is twist an orange thumb screw on the sleeve of the device while simultaneously pushing up on the leg. And just like before, once you're at your new height, stop pushing up and it will lock itself into place just like before.
In order to meet our strength criteria, our device must experience less than 8.75 kilograms per square inch of von Mises stress when exposed to loads ranging from 100 to 250 pounds. When simulated in Autodesk Inventor, our device exceeded expectations by maintaining a safety factor of 10 with loads ranging up to 400 pounds. We also tested the device's adjustability with a 3D printed half-scale model. The model was able to adjust 5¼ inches and remain in place at 21 half-inch intervals of leg. When scaled up, these measurements fulfill the criteria of our design.
As you can see, LegUp meets all of our criteria when compared to our market competitors. It is able to fully support a required weight of 250 pounds. It can adjust to 21 half-inch intervals on a 10.5-inch range, and it does not pose any extra hazards to the user, whether that be laceration or puncture. It is also able to fit onto any Type 2 or Type 3 ladder. From the table, you can see that all of our competitors failed to accomplish at least one of these tasks, making LegUp more desirable to the user. Our material of choice was aluminum 6061 with the heat treatment of CT651. This heat treatment is the most versatile and will help aid in the corrosion resistance. Aluminum 6061 is durable over repeated use and will not rust when exposed to outdoor elements, which is important considering our device will be used outdoors. We needed to accommodate our customers' needs when choosing our material, therefore it had to be cost-effective. Aluminum 6061 is relatively cost-effective compared to most of our other competitors. This is also the material that typical ladders are made out of, not only proving its effectiveness, but also ensuring that no corrosion exists between the metals. As an added benefit, aluminum 6061 is lightweight and portable, making it more accessible to the user. Our manufacturing methods of choice were a combination of CNC machining and sheet metal welding. Computer numerical control is a simple way to make a quick, repeatable product with minimal room for error. We are also able to directly upload our CAD drawings into the programmer to have them printed. Our other manufacturing method of choice was sheet metal welding. This is an inexpensive way to make accurate and strong pieces as a result. After soliciting manufacturers, we came up with a production price of $6,406.61. This was an estimate given to us by Proto Labs. This is very expensive because it does accommodate for all pieces being made from CNC machining and the creation of the molds as well as the product themselves. From this, we realized that we need to make our device more manufacturer-friendly. Things such as 90-degree angles and custom pin sizes add to an unnecessary increase in the cost.
Due to our safety factor being much higher than our criteria, we could reduce the density of the product to lower costs while maintaining functionality. The method of attaching to the ladder leg also needs further development and testing to ensure that it is safe for the user. Potential additions include a safety strap to help tie the leg in place and supports for the platform to prevent any bending.
As we conclude, I'd like to give a special thank you to Mr. Cahoon, Mr. Hill, and Mr. Bernstein for helping us through our progress in this whole task, and especially to our mentors, Mr. Howard and Mr. Kelly. Without them, we would have been a lot stuck on plenty of different things, so thank you to all of them.
Well, I will say that was a good presentation overall. I liked it. My own question is, did you do any testing at all, like functionality-wise, like have other people try to apply it and see if they could figure it out?
So we never did do any testing to see if any other people could try it, but we do have a working prototype right here. If you'd like, we can hand it down to you, or I'll have Mr. Cahoon hand it down to you. You can play with the functionality. It does function like our actual device would, but we've never had anyone actually test it just because it's made of plastic and you're worried about it potentially breaking.
Okay.
Agree with Bailey. That was an excellent presentation. Questions for you. Can you explain safety factors and the safety factor for what went into determining that?
So a safety factor of 10 means that based on the simulation results, it could withstand 10 times the force that it was experiencing without going past the point of permanent deformation. So that safety factor means that even if it's experiencing loads more than what it's designed for, it'll still be safe for the user. And that is based on the aluminum 6061 material ultimate strength.
Very good presentation. I think I missed something as you were going through. You said the increments are half-inch or quarter-inch? Because I thought you said half, but it looked like it said quarter on the slide.
Yeah, so the increments are half-inch on our actual product, but the one that we tested was quarter-inch because it was a half scale.
Do you think that half-inch is enough? Is small enough?
So that was one of the things we actually spent lots of time designing or just thinking about, because there's so many different alternating surfaces. We really can't have exactly all of it. And with our strength factor, like needing to be so high, if we were to make our little barbs on our leg any smaller, there could be the potential for bending and breaking. So that's why we went with the half inch, because it's just ever so slightly thicker than a quarter inch, because we didn't want our thing to break. But seeing that our safety factor is so high, maybe in the future we can make more precise iterations.
Okay.
Structural damage, a homeowner's nightmare. Overflowing gutters can be the source of many issues, such as damaged siding and cracks in the home's foundation. And prolonged water exposure can be the cause of leaks within the home.
Now cleaning your gutters yourself is always an option. However, it can be dangerous. In 2020, approximately 80,000 people fell and were injured while cleaning their gutters. Gutter cleaning services can be expensive as well, costing nearly $210 per cleaning. Normally, cleaning is required at least twice a year, and the cost can vary depending on the square footage of one's home. However, paying to repair damages or replace gutters can be even more costly.
OSHA requires that fall protection be provided at elevations of 6 feet and above. On average, gutters are mounted structures 11 to 19 feet above the ground, which exceeds OSHA's regulations for maximum height without protection. Annually, around 80,000 people fall and are injured from gutter-related falls. Oh, no. Mind if I restart? OSHA requires that fall protection be provided at elevations of 6 feet and above. Gutters on average are mounted structures 11 to 19 feet from the ground, which exceeds OSHA's regulations on maximum height without protection. Annually, around 80,000 people fall and are injured while cleaning their gutters, and the cost of professional cleaning can be anywhere from 40 cents to 80 cents per linear foot of gutter. Poorly maintained gutters can cause damage to the foundation of the home and the surrounding areas of the gutter.
Our primary goal was effectively cleaning gutters and removing debris and obstruction. With nearly equal importance was effectively keeping the homeowner safe. Thus, this led us to prioritizing usability from the ground. Finally, we wanted users to be done in a time-efficient manner. Thus, usage time was our third most important criteria.
Through our brainstorming process, these were a few of the solutions that we came up with. Firstly, we discussed having a motorized cutter that would roll back and forth through the gutter by breaking up debris to be sent out over the edge. Another solution we thought of was a long handle or pole used from the ground with an attachment on the end similar to the design of a snowplow. The device would be dragged alongside the house and the debris would be sent out over the edge. Lastly, we considered having a cart that would be rolled around the perimeter of the house with a long tube attachment to a vacuum that sits on the edge of the gutter and a basket to catch the debris.
Nearly all homeowners interviewed indicated that they were required to get on an elevated surface to clean their gutters, whether that be standing on the roof, reaching out of a window, or reaching off of a ladder. The most common tools used were a leaf blower or a gutter scoop. Additionally, our market research showed that a gutter cleaning wand was a popular option. It's connected to a hose and it sprays water to clear the gutters.
I'd now like to introduce Gutter Buddy. The Gutter Buddy is a backpack-style vacuum that ensures quick and easy removal of debris from within gutters on one-story homes.
In comparison to the current market competitors, the Gutter Buddy is usable from the ground. It clears obstructions, and it can be used in a timely manner.
We utilize a 5.5 horsepower wet-dry vacuum motor that sits on top of a waste canister. The wet vacuum capabilities allow us to suck up sludge and other wet debris. The device will be worn by the user as a backpack. Once debris enters the canister, it will become noticeably heavier, notifying the user that it is time to dispose of the debris. Located on the left side of the canister is a buckle clip that allows the user to remove the bottom portion that swings open to allow for quick and easy removal of debris. Located on the right side is a 6-foot section of ribbed flexible tubing. In our design, we use similar qualities to current backpack-style leaf blowers to find correct dimensions as well as provide a comfortable fit to users. We utilized a simple waste canister base and added a motor and our other features around it. We dimensioned to allow for ease of mobility and prevent the canister from blocking the user's arms. Our attachable tubing sections allow the user to get any height of gutter, no matter the varying height in your home. These sections will be attached through a friction fit system. Once the desired height is met, we calculated the optimum angle of 42 degrees to reach up and over the gutters to extract all debris inside.
The modulus tubes will be made out of durable high-density polyethylene, while the flexible tube that attaches to the canister will be made out of a softer polyethylene that allows for a greater range of motion. The canister will be constructed out of ABS plastic with aluminum reinforcements, with the portions of the canister housing that will be in contact with the motor made out of a polycarbonate due to its higher resistance to heat. The straps will be made out of nylon fabric and will have added EVA foam for comfort.
The goal of our first test procedure was to verify the ability of a 5.5 horsepower motor to collect debris at a certain weight. To administer the test, we marked 2 pieces of the tape on the ground 6 inches apart. We then created 3 bags of varying weight, 75, 100, and 150 grams, based off of the maximum amount of leaves that could reside in a 3-foot section of gutter.
We then turned on the shop vac and moved the tube attachment closer to the bag until the bag was collected by the motor. We measured the distance and recorded the information based on the weight of each bag. Results showed that the motor was able to collect up to 150 grams of weight with 5 tubing attachments, equating to 11 feet, therefore indicating that our product will be able to clear obstructions from within the gutter of a single-story home.
When designing our product, one of the features we wanted to incorporate was comfort, as the backpack will be worn for up to an hour at a time. To ensure the user will be able to maneuver the backpack without strain, we looked at the average length and width of an adult's back, as well as the dimensions of a backpack and a vacuum backpack, to settle on the dimensions of the canister having a 6-inch radius and being 2 feet tall.
In the future, we plan on having a mirror at the end of the tube, which will allow the user to see inside the gutter and more efficiently clean their gutters. We would also like to expand on two-story homes, which will widen our market.
Now we'd like to offer a big thank you to everyone that helped, and especially Mr. Kuhn.
Yes. All right, great presentation, way to work through it. The challenge with live anything is you have to improv sometimes. But moving forward, you guys did a great job. I have a lot of questions, but we're limited to one. But it's mostly because I'm intrigued by this. Leaves are terrible. What I wanted to ask is, in considering alternatives, did you consider the alternative for non-leaf removal and leaf prevention capabilities? And can you talk a little bit about that?
Yeah, so we did look at gutter guards, and we realized that those are like a really popular item, and a lot of homeowners already have those. So we were looking at more removal methods. One of the issues that we came across with gutter guards is that leaves can stay on top of the gutter guards, so like there still will be some blockage. So we decided to go with a cleaning method instead of a prevention method.
Okay, and I lied, I'm gonna ask one more question if that's okay. So in considering your testing and your various weight payloads that you were removing with the vacuum, did you consider wet leaves, pollen, and pebbles from asphalt shingles?
Yeah, so we had a wet vacuum motor, so that would be able to suck up like the sludge and all the other wet debris. And we had some tests to just be able to determine what load we actually could suck up.
Okay, so in determining the size of the packages that you were testing with, the consideration of leaves per cubic inch or whatever, that was wet leaves and dry leaves? Okay.
Yes, so we had a 3-foot section of gutter that we got from like Home Depot, and we went outside, got leaves and debris and stuffed it in the gutters to determine like the weight that it would be. And then we just transfer that into bags with like shredded paper so that it was easier to have like a set weight each time so it was consistent throughout trials.
Okay, thank you.
Hi, nice presentation. A couple of questions. How did you decide that 42 degrees was the optimal angle for that hook piece, and have you considered making that adjustable?
Yes, so we did consider it being adjustable. That's in our future iterations. And we got that 42-degree angle by taking the average length of a flower bed. So when cleaning your gutters with the Gutter Buddy, you'd have to be standing in front of your flower bed, so that's about 10 feet, and the average height of a one-story home's gutter is 11 feet. And we just did basic trigonomic functions and found an angle of 42 degrees.
And it isn't clear to me what the backpack is going to look like, so that looks like a very heavy wooden or metal thing, but your diagram, your picture showed an actual backpack. So what is the material going to be for the back unit, and how easy is it to clean it out when it's filled with all the sludge and stuff?
So the actual canister portion that resides on your back will be made out of mostly ABS plastic. It's going to have aluminum reinforcement, and the portions that are in contact with the actual motor is going to be polycarbonate because the motor will get hot and we need something more heat resistant. This was just, our prototype here was just a rough kind of show the concept, since we couldn't have access to large amounts of those materials.
And for clearing the leaves, there's a latch on the bottom of the backpack that you open, so allow leaves to fall out the bottom, and you can just empty them into like your average brown bag that you put leaves in, or a garbage bin. And to ensure that it doesn't get on the user, the entire bottom does not open, half of it opens, and the other half is going to have an angle on the inside so that all the leaves will empty but not on the user.
Good, thank you.
So what is the diameter of the tubing that you guys are using? And how did you come up with that? Because like, I know at least with wet leaves, they kind of clump up a lot more. So are you able to actually get that in, or is it more like you grab it and kind of pull it off?
So the diameter of the tube is 2.5 inches. We picked that diameter because it has the, so as the diameter of the tube increases, we lose suction. And 2.5 inches was just big enough to be able to fit our leaves through it. The suction should be powerful enough to where if you have a wet sludge of some sort, it can suck it straight down into your back canister.
It is tough to be a chicken, though. As we said, foxes, snakes, and opossums can pose severe threats to chickens. In a survey of over 100 Maryland chicken owners, nearly 3/4 of respondents said that their coops have been attacked by predators at some point. Now, there's a number of reasons why predators might be attracted to coops. Maybe there's food in the rut or something similar. But another large factor is eggs left in nest boxes. In the same survey, the same proportion of chicken owners said that they had left or forgotten eggs in their nest box at some point. Now, for point of reference, a nest box is a small compartment within a larger chicken coop in which a chicken lays her egg. The issue arises when homeowners forget these eggs within these nest boxes, which leads us to the problem at hand.
When left out in the chicken coop overnight, residential chicken eggs attract predators such as foxes and possums. As a result, these predators are almost twice as likely to attack a nest with eggs than without. This is concerning because upon attack, such predators have been reported to kill up to 12% of residential free-range flocks.
The current solutions on the market, seen here, all attempt to solve this problem. Their methods range from AI detection to roll-away nest boxes, each with a unique flavor of failure. Some are too costly, some require replacing the entire coop to install, and some are simply too inconsistent to rely on.
With this vacancy in the market, we bring you the DET-EGG-TOR. I'm Sadie Fishburne.
I'm Chloe Evans.
I'm Amelia Farrar.
I'm Johnny Kraft.
And I'm Heather Tweed. Our top criteria for this project started with animal safety. Neither the chicken nor the egg could be harmed. Up next was the performance. We wanted a product which could alert a chicken owner of the presence of an egg within their chicken coop. Adding on to that was the connection to outside devices. We needed it to connect to a device which could alert the chicken owner that it was time to collect the egg. Lastly was the size and weight of our product. It needed to fit into the average chicken coop as well as hold both the chicken and the egg comfortably.
Through the design process, we considered alternatives using thermal imaging, weight scaling, and locking devices to keep eggs contained. However, when looking further into these solutions, we found that thermal imaging would be immensely costly and performance could be affected by hot days. Problems arose with our weight scale designs, as weight scales often miscalibrate after long and constant uses. And finally, our locking device performed poorly with animal safety, as it poses a threat of breaking eggs when the locking door was closed.
As you can see, a lot of our initial ideas were heavily rooted in and dependent on technology. For this reason, we decided to build off of the roll-away nest box design to improve upon the most basic aspect of the modern nest box, the structure. Most nest boxes are just that, a box. Where our product differs is in the ramp and collection area. Once the chicken lays her egg, it rolls down the ramp and into the collection area where a hinged door makes it easily accessible for the owner to collect at their earliest convenience. But structure alone is not enough to improve upon a product as a whole.
This is where the Arduino comes in. The circuit itself is simple. One force-sensitive resistor placed in the center of the egg collection area is used to measure weight, and one LED is used to notify the owner. Every 20 minutes, the code reads the force sensor input. If it is above a certain value, calibrated for the weight of one egg, the LED will turn on. The LED will turn off if, on any rotation, the weight is below one egg, or it exceeds that of one chicken, to prevent them or heavier obstructions from sending a false alarm. To connect our circuit to the box itself, we 3D printed a base to hold the Arduino. Of course, exposed wiring can easily be damaged by adverse weather or the chickens themselves. To combat this, we 3D printed a case as well, to hold the electronics with 2 holes for power and wires. Of course, any box, ramp, or casing has to be made out of something.
And we started with a wooden base. In specifics, outdoor plywood. We chose this due to its lightweight and cheap cost. Up next was a poly-like synthetic turf, which we chose due to its short-hairedness. This allowed for the egg to keep rolling all the way down the ramp into the egg collection area. Lastly, for the curves added to the inside of the box, as well as the Arduino case, we used polypropylene plastic. This is one of the top animal-safe plastics, as well as being durable and heat-safe.
As some of our peers initially had a couple of concerns about the comfort of chickens within these nest boxes, so we had our brave volunteer Ruth test out the animal safety of our fully built DET-EGG-TOR prototype.
Now, our first test was the ramp height test. We needed to make sure that no matter where the egg was laid on the ramp, it would make it down into the egg collection area. We tested this by placing the egg in 3-inch intervals all the way down the ramp. Sadly, our first attempt at this failed due to the fact that the egg kept getting stuck on the inside walls of the nest box. To combat this, we added the plastic curves. This lets the egg keep a continuous rolling motion all the way down into the egg collection area.
Our second test was the material test, which evaluated different materials' ability to cushion the egg within the egg compartment. Through this test, we found that all tested materials were able to sufficiently cushion the egg, which means that we were able to choose a cushion material based on different factors. We chose dry, fast, open cell foam as it scored highest on our material decision matrix.
Our third and final test was the Arduino test, conducted to ensure the LED would only turn on when it detected between one egg and one chicken. We did this by placing a plastic egg directly on the force sensor, with controlled weights going up and through our two weight ranges. While it took a few calibrations to get correct, our current circuit passed the test.
Now, in the same survey that we mentioned previously, 45% of respondents mentioned either broody hens, or chickens that sit on their own eggs, or chickens pecking their eggs as issues that they face with egg collection. The detector was built with these issues in mind and is able to combat both of them. By using the egg collection area, chickens are physically unable to sit on their eggs or peck at them. Now, comparing our product to some of our competitors, the rollaway nest box, the egg glue cube, and egg sighting all just fall short of notifying owners in an affordable fashion. The detector, however, is able to keep chickens safe while keeping hens, their eggs, and their owners in sync.
The detector will be sold for $95, which will account for both material and production costs, as well as a 60% markup based on similar pet supply trends. Shipping will be an extra cost to the user, and domestic shipping ranges between $15 to $25.
Moving forward with this project, we would firstly like to develop an app that could be connected to the Arduino to notify owners of how many eggs are in the nest box, as well as how long they've been waiting to be collected. Once the app has been developed, we could look into getting cheaper breadboards that don't contain the unnecessary and unused components found on our current breadboard. Additionally, we do have to update some of the dimensions of our box, as this was just an initial prototype.
I'd like to extend a very warm thank you to all of our teachers, including Mr. Cahoon, Mr. Bernstein, Mr. Hill, and Mr. Mordo, as well as our mentors who were extremely helpful, and the chicken that did volunteer for this. I'd like to turn it over to our panel of judges for any questions, and thanks so much.
Nicely done, guys. So mine's going back to testing. I loved how you tested it, but my only question is, did you test with an egg already there? Like, you test it rolling and cracking the egg as it hits another egg?
Yes, that was part of our materials test. We rolled the egg down the ramp that we had already tested before and ensured that it would not crack. That's how we chose our materials.
No, great presentation. I know very little about chickens other than they taste like. The ramp and the angle of the ground for a chicken, does that have any impact on their ability or interest in laying an egg? And was that factored in as far as doing some type of chicken animal preferential research?
Yeah, so that's a great question. So that was one that was brought up a lot when we first decided that we were going to have the inclined plane as sort of our design. And if I could, I'm just going to circle back really quick. Sorry, I have a lot of transitions to get through. We did test that. I raised chickens. This is one of my own chickens sitting in our prototype. She was able to get in and was there. I mean, I didn't wait for her to lay an egg, mind you, but I mean, the research that we did shows that chickens are able to lay eggs on slightly inclined surfaces that are, and this is a 12% angle based on our dimensions, so it would be not an issue for chickens laying eggs.
And we were going to test a couple different angles for that ramp, but we decided that, well, we found out that all of them actually do work. So we decided to just go with the industry standard, which is 12%.
Okay, and then one really quick question. As far as power goes, do most chicken coops have like AC power, or is this battery powered?
Yes, most coops actually need heat lamps in the winter to keep their chickens warm and safe during the winter. So we decided to target the audience of chicken owners that already have power supplied to their coop.
Excellent presentation. I think Chubb's coming up with a question. So with the ramp, my image of chicken coops is that they've got like hay or straw or something that they nest on. So will they get used to just having that turf material?
Yeah, so basically, a lot of chickens, Chicken coops vary, and that was an issue with coming up with a prototype, is we wanted something that could fit any chicken coop, and the paddings that people use for their nest boxes also vary. Turf is a very, very, very common one. Straw and hay are as well, so any real, padding of any kind, you can use a rubber mat, would be comfortable enough for a chicken to lay an egg.
And is the material on the ram removable so that you can clean it?
Yeah, so that was a big part of our choosing which padding to use for the base of our ramp. We didn't want to use anything similar to straw or hay for that reason, because that would be difficult to take out and use. You'd have to just dump it out and put new shavings in. So we wanted to have something that was synthetic so that you could take it out and clean it. Being able to take it out, we haven't fully developed that yet, but that was absolutely something that we were considering moving forward.
Thank you.
1.3 million people in the United States have limited grip strength due to rheumatoid arthritis. More than 8 million people are affected each year by carpal tunnel syndrome. And roughly 35% of older adults in the United States are affected by sarcopenia. This is a familiar picture. An elderly woman is struggling to navigate her daily life trying to use a rollator. We all know someone who struggles like this. So what are the characteristics of one of these devices? A rollator is an assistive walking device that consists of a frame with 4 large wheels and a braking system. They can assist with daily tasks like walking and keeping balance while moving.
The most common problem we discovered while researching rollators was that the existing market rollators require approximately 7 pounds of force to fully engage the braking system. And users with limited grip strength report having difficulties enabling the brakes.
After conducting problem interviews with people ranging from 30 to 100 years old, the biggest problem we found was that 44.4% of interviewees experienced difficulties engaging the brakes. As this compromises safety, a key feature for rollators, we knew we needed to tackle this problem.
Hi, my name is Paige, and these are my teammates, Christina, Julia, Francisca, and Isabella, and today we are excited to bring you Rollamax, the newly designed mechanical braking replacement for rollators to help those with limited grip strength use the rollators in a safer and more comfortable way.
During market research, solutions range from a vertical brake handle with armrests, a push-down brake rollator, an external friction wheel stopper, and a foam handle attachment. Although these solutions aid with hand positioning and ease of function, they either require the entire braking system to be replaced or do not reduce the force required to enable the brakes.
From our market research, the following criteria was established: ensuring FDA approval, enhancing the functionality by engaging the brakes with less than 7 pounds of force, and maintaining durability after consistent use.
Our first ideas included a variety of solutions, like an electronic switch motor, a mechanical slider, a pull string design, and a mechanical button.
We also considered rerouting the brake lines. However, this would not allow for the easiest implementation in factories and increase the cost. We concluded it would be best not to alter an already universal braking system, but rather improve and design a replaceable handle. This handle would require less grip strength by using the mechanical advantages of a longer handle.
Our first prototypes, as shown on the slide above, were designed as second-class levers, simple yet effective. These were not the most comfortable, however, they did help us determine the correct placement of the screws and the distance they would need to be inserted.
Here's our process of trial and error, where we continue to 3D print, test, and redesign. Each iteration adapted to new challenges like material density, hand placement, and thickness of handle. Although these changes in each iteration seem relatively simplistic, they made certain that small details like tolerances and spacing of features fit precisely with the current braking system.
After altering numerous 3D printed prototypes, we created the final Rollamax handle, effectively reducing the grip strength needed to apply the brakes in the most comfortable way. Rollamax caters to people suffering from limited hand mobility and fits universally all hand sizes. Our design incorporates a 1-nodule grip, a wider gripping area, and an 8-inch handle. The finger grips are intended to fit up to the 99th percentile median finger width of adults over the age of 65.
To achieve our goal of reducing the force needed to pull the handle, we lengthened the original Invacare model from 6 to 8 inches. The extended length increased the handle IMA, ideal mechanical advantage, by over 30%, from a value of 12 to a value of 16.
Why is our design optimal?
Not only does Rollamax effectively reduce the required hand force by 68% from 7 to 2.2 pounds, we also considerably reduce the finger travel distance from 3.3 to 2.7 inches. This is a key component for those suffering from carpal tunnel and arthritis, as they often struggle to contract their hands to comfortably squeeze the brake handles.
Our test involved numerous components in order to reduce as many outside factors that prohibited accurate results. We created a stabilizer system that ensured the rollator stayed in one place using ratchet straps and 10-pound weights. We then used a pulley system consisting of a wooden rod and 8-pound weights and a luggage scale, which ensured the force applied would be perpendicular to the metal frame. The attached scale measured the force required to gauge the brakes on both the Invacare model and Rollamax.
Rollamax is durable, water-resistant, and UV-resistant. Users won't have to worry about altering their lifestyle in exchange for comfort. We conducted an FDA stress test on our prototype and attained a value of over 15,000 megapascals around the screw hole, which is incredibly high. The tensile strength of high-density polyethylene is 20 to 40 megapascals. As there are few materials that would be able to withstand the level of stress we calculated, we believe that the test was performed incorrectly. However, we only recently began to perform these tests and plan on gaining more knowledge and familiarity with the software in order to perform an accurate FDA stress test in the future. As you can see, Rollamax meets all the important qualities of a handle compared to its competitors in safety, accessibility, and effectiveness.
Rollamax will be constructed out of HDPE plastic through injection molding. It is environmentally friendly, durable, and cost-effective. It takes minimal energy to construct, and HDPE is the safest material to develop a handle with.
We ran Rollamax and the existing Invacare handle through an injection mold calculator, and the final cost came out to be 29 cents per unit for both models. This confirmed that replacing existing handles with Rollamax significantly improves the ease of use of a rollator without increasing the cost to the company. The ultimate goal for Rollamax will be to license our product to a manufacturer where they will install the handle to the rollator frame themselves. Rollators with Rollamax are still FDA approved to ensure that most insurance companies will cover the cost, including Blue Cross, Medicare, and Medicaid. Moving forward, we would like to add an extra feature to give users a more comfortable product. For this, we are planning to add dicing around the handle, which is a flexible, non-slip material to add extra grip for user stability.
Thank you, and we hope you consider adding Rollamax to improve your next assistive device.
So the white one that you're being cast right now is our first iteration, and the green handle is our latest model. It's our final product. Nice job, guys. All right, so my first question is going to go back to the injection molding cost. What sample size did you guys use for that calculation? Because I know injection mold, like the molds themselves are very expensive at the beginning. So is the number that you use like realistic to your audience or no? So we calculated it using an injection mold calculator, assuming 100,000 to 300,000 molds would be printed at a time. And it already accounted for HDPE being the material used.
And then my other one was with the design itself. Did you guys design around like one specific roller type, or is it adjustable for like different rollers, I guess?
So we worked around the Invacare model, which is a closed frame rollator, and it is not adaptable to other rollators. However, that's a future iteration, and we have done our measurements, and it won't stick out past the end of the frame of an open-handled rollator, which is very important because then that would reduce our effectiveness. So we have done the measurements.
Great job. It's nice to actually see this come to fruition throughout the process. I know you guys went through quite a few different approaches. So anyway, question regarding FDA approval, because that was one of your stated exit criteria or focuses. The cost associated in the process in getting FDA approval, is that being factored into the price per unit, or is that simply production? And then can you talk me through the FDA approval process?
We have not looked into the cost of FDA approval with the unit cost of 29 cents per unit. That cost is just strictly the cost that would be applied to manufacturers. But for FDA approval, I'm not 100% sure about FDA approval.
Okay, and then the follow-up question, the 2 10-pound weights to keep the rollator stationary during testing. Can you explain a little bit how you came up with the 10-pound weights?
So we designed the stabilizer system kind of through a process of trial and error. So we just wanted to create a system that would keep the rollator in place, and by using 2 10-pound dumbbells with a ratchet strap, it kept it in place and completely stationary because we knew that the force we would be applying would not be greater than 20 pounds.
Okay, thank you.
Really nice job. I just want to go back over another question that Bailey asked. So this is designed for a specific model of rollator. Can it be adjusted to fit with other brands, or because I would imagine the handles are brand specific in terms of their function and size?
So they are, this one is specific to the Invacare model. However, due to like the slight changes and like the tolerances in each handle that are slightly different, we feel that it would be very easy to change the specific like screw dimensions and the sizes to fit open handle rollators. There's Drive Medical is a very common one, and those were the ones that we were trying to compare the most to, because since that's the one that we see a lot of people and users use, it was definitely something that was comparable. However, this one is specific to the Invacare model.
Okay, thank you.
I have 2 things. One, we need to take this further. People are willing to spend a lot of money to comfort and aid their elders, and there's not a lot of things out there to do that. So people will buy a product like this, just flat out. So you need to work on that. Second of all, it's totally okay to say you don't know the answer, and not everyone does. But just for everyone listening, be confident when you say that and word it in a way that just says you're not comfortable to make a decisive comment on it at that point, right? So instead of being like, I'm not really sure, just be like, I'm not confident in providing the answer on that right now, right? Well, it's cool to not know things, not everyone does. This has happened to me a lot, but if you change the way that you're wording that response, it gives you just a little bit more credibility, and you guys were so confident through this entire presentation. So you don't lose that, just being caught off guard.
Have you ever tried to pour a cup full of water and it ends up trickling down the side of the container, resulting in a spill? This phenomenon is known as liquid adhesion, or the attraction of a liquid to the outside surface of a container when pouring. And while it may just seem like a slight annoyance, liquid adhesion poses a major threat in laboratories because it can lead to spills of unsafe chemicals and inaccurate data collection. With over 153,000 labs in the United States, there's a large market for a device that would fully prevent liquid adhesion in labs. Liquids with a viscosity between 1 and 85 centipoise tend to stick to the outside of glassware in labs when being poured at an angle and speed that are not optimal to overcome the liquid's adhesive effects. To simplify that, we wanted to develop a solution that would fully prevent liquid adhesion in labs. We interviewed a large group of people from many different backgrounds, all of whom had lab experience. 80% of them said they had experience with liquid adhesion in labs, and 75% said they would like to see a solution. From our interviews, we determined that a solution was necessary. They would need to fully prevent adhesion to the outside surface of the glassware. It would need to be used by only one hand, and it would need to be inert to all chemicals in a laboratory.
Some already existing solutions are glass beakers, which have a spout on them. Now, liquids, especially water-based liquids, can have strong adherence to glass, which causes issues with this built-in measure. There's also glass rods, which are used for decanting, which is when a scientist uses adhesion to pour liquids. This becomes inaccurate when you're pouring at high speeds and can make pouring large amounts or dense liquids difficult. And also funnels require the user to pour liquids into them, which doesn't solve this issue. Some other designs we considered were a hydrophobic cover over the lip of the container to allow the liquid to pass quickly into the container and counteract gravity. We also had a spout with a hinge to guide the liquid into the container and break any surface tension. And we had a compressible lid with a spout to provide an accurate pour.
I'm Nick. I'm Morgan.
I'm Owen.
And I'm Aaron, and we're proud to bring you AntiHesion, an attachment for common laboratory glassware that prevents liquid adhesion and makes liquid transfers 100% safe. For materials, we decided to use polypropylene and 15A shore silicone. Polypropylene is one of the cheapest and most inert plastics on the market today. Silicone allows for the device to wrap around the curvature of the container and creates a nice seal to prevent any dripping. Silicone also has great durability and great compressibility, along with good chemical resistance. Silicone also has a high heat tolerance, meaning that the device can be attached to hot labware. Both these materials are also recyclable. So to use the device, you want to take it and a cable tie. Wrap the cable tie around the indent, as you can see. You then want to put the beaker in between the two of them. Slide the device up and make sure that the top of the device matches with the lip of the container. After that, you want to tighten the cable tie. Make sure it is firm and you're all set to begin pouring.
The main features of the device start out with the 2 points on the side, which are used to cut off the flow of the liquid that is being poured. And on the slight instance that any liquid does get past the first point, the liquid should adhere to the side of the curve and it will be cut off by the lower point. The indentation on the bottom is used to hold the cable tie in place, which will allow the device to be held securely against any glassware that is being used. The silicone allows the device to conform around the glassware so there's no gaps in between the glassware and the device. And the T-shape mechanically locks the silicone into place so the silicone cannot be removed. And on the top of the device, it is sloped inwards so that any liquid that's being poured will be poured accurately into a container.
Our competitors our top 3 criteria was to stop adhesion to the outside surface of containers, be used by one hand, and be durable. Funnels, they may stop adhesion to the outside surface. They may not stop adhesion to the outside surface, and they need 2 hands to be operated, but they are very durable. The spout on beakers, they don't stop any adhesion to the outside surface. They do allow for one-hand pouring, but they are not durable. Glass rods, for decanting, they stop adhesion to the outside surface, but they need 2 hands to be operated, and they are not very durable at all. AntiHesion covers all these bases, and as it fully stops adhesion to the outside surface of containers, allows for one-hand pouring, and is extremely durable.
Before we started testing, we would have to create 3 mixtures, always starting out with 100 milliliters of water and varying amounts of cornstarch. And then we would mix the 2 together to create 4 different viscosities of 25, 45, 65, and 85 centipoise each. And then when we conducted the testing, we put 100 milliliters of each mixture into a beaker with the device attached. We pour out the mixture into a separate beaker, and we would weigh the initial and final weight of the mixture in grams, subtract the final weight from the initial to find the loss of mixture during the pouring process. And with a roughly $1 manufacturing price and 200% markup, we can sell our device for $3.22 to the consumer.
For future designs, we want AntiHesion to be more stackable so that it can be more easily stored in laboratories. We also want it to be able to be made out of different materials because our current materials only cover a certain range of chemical resistance, and we want to tailor AntiHesion for specific circumstances. And lastly, we want to expand our design so that AntiHesion can be used for containers of different shapes. We want to thank our teachers, our mentors, and the individuals who helped us create AntiHesion. Again, thank you for your time.
Okay, great presentation. Based on cost comparison, the cost to produce, is this well within the realm of, additional equipment that, a lab might purchase for, any size beaker apparatus? I mean, I'm so out of my league on this. As opposed to putting it through like a steam cleaner or something like that to clean off, whatever adheres to the outside of the beaker. Does the cost? I don't know. Is this something that people would buy, or are the test tube or the tube rods, are they similarly priced? Are they expensive?
So so it is competitive with our competitors. So glass rods, they're between like $3 and $5. So it's like on the lower end of glass rods. Funnels can actually be between like $5 and $10. Some are a little bit cheaper, but that's what we found. So it's actually like in the middle, kind of. So it is competitive with all of them.
Okay, and then is there a maintenance cost associated with treating the apparatus that you attach, the adhesion or anti-adhesion?
There is no maintenance cost. I would say you can just run it through the dishwasher, or you can rinse it off. You can do whatever you want. There's no one would like you want you to pay to wash it or anything.
There's no coating or anything like that would need to be replaced on it.
Okay, and then finally, attaching it to the test tube, different methods as opposed to zip ties. Can you kind of explain what you looked into?
We looked into having something like an elastic or something that could hold it on tightly, but we decided that using it's a reusable cable tie, so it can be taken on and off and put on different containers, and we just chose that because it could be tightened securely to different sizes, diameters of containers.
And that would also be dishwasher safe?
Yes.
Thank you.
Okay, one thing is when you're introducing new units of measurement, take a second to explain what that is, because I think it was Centos.
Centipoise.
Centipoise, that's something I'm not familiar with. I don't know if everyone else is, if you guys are using that a lot. But just a little blurb at the bottom, this is what this means. So that when you use it throughout the rest of the presentation, you've already explained it. Also, you talked about wanting to be able to use one hand for your product. Did you consider that your hand would need to be, in some cases, sterile? So you would have a component on your gloves, a mitt. There's other things in a laboratory that you have to put on in order to keep yourself safe. Did you weigh any of those when you were testing?
So for testing, it's common in laboratories that you would always be wearing gloves when you're handling any chemicals. But for let's say our competitors using a glass rod, you would have to you'd have to hold the glass rod with one hand and then have your another hand on the beaker. And there's other ways to do the configuration. You can have like the glass rod inside the container, pour it out, but it increases the risk of it getting on your gloves, and you wouldn't really want any chemicals on your gloves anyway, along with the fact that the liquid can get underneath onto the surface that you're pouring over. So our device securely attaches to it, so you literally can use one hand. If you're dealing with a heavy liquid or dense liquid, you can use two hands safely. No chance of spilling at all.
When you did your testing, you talked about how you tested and then poured the different viscosity liquids into the other container. Did you get 100%?
Yes,
What were the results?
we had 100%
For all of them?
success, yes.
Okay. So there's no residue left on the surface of the product?
No.
No, okay.
And for our testing criteria, 2% we weighted, and 2%, if it was less than 2% after it was poured, then it would pass.
Okay. So my other question was about cleaning, which we talked about. And the other question I had was about stability. So in a lab, you'll have a big beaker, but you'll also have, smaller beakers for smaller containers. Can it be scaled down?
So the purpose of our device is to be used, so we only tested it with just 250 milliliter beakers, but we want to in the future test it with like a little smaller, a little bigger, just to ensure that it works for those sizes. And then we can like build up and do for like flasks, maybe expand in our design. But yeah, we do, it should work for containers that are around the same range, but yeah.
All right, so my final question is also to do with testing. So you said it worked 100% of the time. What was the data looking like for without your product on it? Like, did you run the same test with the beaker itself?
We did not, but from what we could tell just from regular research, there's a lot more adhesion that occurred down the side of the beaker.
I want to add on that we didn't do official tests, but I did get funnels and glass rods, and I did experiment a little bit, and I was able to get successfully the liquid to go onto the side and here to the beaker using all three of them. So.
And then the other one I had was about the injection molding costs and everything. What value did you use for like unit and is it one piece together? Is there two pieces?
So we're going to have so it's going to be injection molded with polypropylene first, and then the silicone is going to be over molded onto that. And using our injection molding calculator, we did the cost of both of them separately, and that's how we did it.
Raise your hand if you've ever ordered a package online. Now keep your hand raised if you've ever had a package stolen from you. You're not alone. 3 out of 4 Americans have a package stolen from them at some point in their life. And this metric only gets denser as you head into urban populations. Over 90,000 packages are stolen every single day in New York City.
In the past year alone, over 260 million packages, collectively worth more than $19 billion, were stolen off of doorsteps. Common methods to prevent package theft, such as surveillance cameras, only function as a deterrent to theft and are ineffective in preventing it. Row home residents in cities are especially susceptible to having their packages stolen because of small porch sizes and doors close to the sidewalk. In order to solve this problem, our group created P-Cubed, the Porch Pirate Preventer. Prior to creating P-Cubed, we interviewed apartment and row home residents. The majority of our interviewees had a medium-sized package stolen, which is here on the table, the FedEx standard 12 by 12 by 18. We wanted to base P-Cubed to fit these measurements.
When looking into existing theft prevention methods, we looked at everything from die packs to magnetic sensors, but we discovered P-Cubed has 3 main competitors. Firstly, the Ring doorbells. a surveillance camera for the front porch. Second, the delivery safe, a large lockable drop box that gets placed just outside the front door. And third, the Amazon key, an installable lock that allows certified delivery drivers direct access into the home to place the package inside. Now, we wanted to set P-Cubed apart. To do that, we needed to make sure P-Cubed was secure. It needs to be able to hold a 12 by 12 by 18 package, only be accessible to the homeowner, and not give the delivery driver access inside. Also needs to be durable by maintaining IP55 dust and water resistant standards. And third, it needs to be easy to use for both the homeowner and delivery driver, keeping the overall delivery time less than a minute, and the device should not obstruct the entry to the home.
Keeping this criteria in mind, let's take a look at our competitors. The Ring doorbell fails in its security of the package because being caught on camera is often not enough to stop theft. It acts as a deterrent rather than a prevention method. The delivery safe fails in its ease of use. The large size of the Dropbox impedes the average entryway of a row home. Finally, the Amazon key also fails in its security because it allows the delivery driver complete access into the home. Unlike our competitors, you will see that P-Cubed meets all of our criteria.
Before landing on our final idea, we started with our preliminary designs. One of our designs was the pressure plate. The plate, when the package is taken off by anyone other than the recipient, an alarm will go off. We also considered the package vault, a large lockable box outside the resident's home. We even considered camouflaging our package as a pod plant. P-Cubed has three main components: the drop door, the plastic flap, and the electronics box, controlling the locking mechanism of our door.
The drop door, the central component of P-Cubed, is a 14 by 14 8-inch thick aluminum sheet with a handle to pull down. Around the perimeter, there is a rubber gasket to seal out any external weather conditions from the inside of the home. There is a metal D-ring allowing for a strong connection with the solenoid lock. And there are springing hinges, which will automatically close the door to the locking position once the delivery driver has dropped off the package.
Additionally, there is an acrylic plastic flap on the back side of the door with hinges that allow for 90 degrees of motion. That way, the delivery driver cannot reach into the home, and any pets the homeowner may have won't be able to escape. There's a small slit on the top to fit the solenoid lock.
The electronics component of our design utilizes a button, an Arduino Uno, a 9-volt battery, a relay module, a solenoid lock, and a 12-volt battery. Our design will utilize RFID. The delivery driver will scan the package, sending a unique signal to the RFID reader, which then unlocks the solenoid lock for a duration of 5 seconds before re-engaging.
In this video, you will see the package deliverer scanning the package, approaching P-Cubed. P-Cubed will disengage. He opens the door, pushes the package through past the plastic flap. The lock will re-engage on its own, and the door will close. Now our porch pirate comes over, can't even open the door.
Our first prototype tested the security aspect of P-Cubed. It was made of a plywood model door that had a 14 by 14 inch opening located in the center, 16 inches from the bottom. Participants were instructed to reach through the opening towards an interior doorknob, and 4 of the 5 participants were able to reach the doorknob, thus failing our test. Based on these results, we decided to move the opening to the left, which would be opposite of the interior doorknob, and we also changed our dimensions to 13 by 13 inches, which would still allow for our package size requirement of 12 by 12 by 18 inches.
To be sure P-Cubed met IP55 dust and water resistant standards, we added the rubber gasket, which creates an airtight seal, and we also ran this test on the gasket using a spray bottle to simulate rain, and as you can see, no water went through.
P-Cubed costs $11.35 to manufacture. With extra costs from installation and the exterior door and a market standard markup of 50%, P-Cubed comes out to $1,914 to the consumer.
In future iterations of P-Cubed, we would recess the drop door to prevent any prying from the outside and create a cleaner, sleeker look. We would use rivets instead of screws on our external springy hinges so they cannot be unscrewed from the outside. And we would partner with companies such as USPS and FedEx to utilize their current infrastructure and put RFID scanners into their current scanners.
Rest assured, you're secure.
Alright, well, presentation looked great, and the test looked good and everything. My issue just kind of comes with the practicality of it, because I live in a row home in Baltimore, and I rent it, and there's no way I can install that on my door. And I have a feeling like a lot of your audience and everything are renters, so they can't really cut holes in their doors. And also that price, I feel like, is pretty high when typically your Amazon packages are like 20 to 30 bucks.
Yeah, so our device, you wouldn't have to cut the hole in the door yourself and install it. Our device is the whole door. If you're going to buy a front door, you would be looking and buy the entire door with our device already installed. That's why the price is so high, because that's also including the cost of the exterior door and installation of that door into the home.
Did you do any, like, I guess, post interviews with anybody to see if people would actually buy this with that pricing?
So officially, we didn't like write it down or anything, but I did ask around my work, and a lot, like 75% of my work lives in Baltimore and has a row home, and they did say that this may not be, it may be a little over-engineered, but it's the safest option that they would be comfortable purchasing.
Great presentation. This is a prevalent problem, whether it's due to stolen packages or just misplaced or lost or misrepresented packages. I know personally we get notifications that Amazon has delivered, yet the package is still en route. So trying to kind of dissect that and figure out if it's truly stolen or it's misplaced, sent to a neighbor. I can't imagine how often they get misplaced when high-density housing is around. My question has to do with the weather resilience. So there's a gasketing around the door, as you presented, but a lot of front doors are insulated. So can you talk to a little bit about the insulation design considerations as it relates to the size of the square?
So that's part of the reason why we chose to do a full door rather than like installing P-cubed, because we wanted to preserve the integrity of the door, not like a homeowner cutting into it themselves. The rubber gasket tape is there to meet our IP55 standards of the dust and the water resistance, which would account for rain or like weather exterior conditions. But otherwise, it shouldn't change the actual installation of like a typical exterior door.
Okay, thank you.
Can we just review the cost of each component? I see you've got a slide there. Because I'm wondering how much, my specific question is how much more does it cost to get this kind of a door with this versus a regular door?
Oh, sorry, that was the electronic sales.
I think P-cubed on itself came to like about $11.53.
Okay.
Yeah, the majority of the costs come from the exterior door. Some interior doors can range just a couple $100s, but with exterior doors, you can see we used just an average cost. We went to Home Depot and Lowe's and looked at just so many common, like low-grade exterior doors, and averaged out to about $500. But that really depends. There's a wide range. So that's where, and the installation as well, because a lot of people will have someone come and install the door for them. So that's where the majority of the cost comes. But as you can see, our device itself that's built into the door is only just over $11.
Okay, so you're showing a markup of the total cost of the door and P-cubed, as opposed to just what the markup would be for P-cubed.
Yes.
Okay. All right, you did a great job presentation.
Thank you.
you or a family member has ever broken a bone, you would understand the struggles of dealing with a fiberglass cast. Connect it wet, your skin becomes irritated, itchy, and over time, a foul odor will develop. Roughly 6 million people break an arm every year, with this standard treatment being a fiberglass cast. However, 85% of these fiberglass arm casts have infection-causing bacteria residing within them. This problem is that patients required to wear a fiberglass arm cast in the short arm variant face the risk of infection when ideal conditions for bacteria growth occur. In order to solve this problem, we aimed to decrease the warm, moist conditions optimal for bacteria growth. I'm Jack Miller. I'm joined by Kyle Jobin, Spencer Martin, Nick Whitaker, bringing you DecaCast, a new medical cast alternative that minimizes the risk of infection due to a broken arm.
When looking to the market, we looked at the standard fiberglass cast. This takes about 30 minutes to apply, 2 hours to harden, and has ideal conditions for bacteria growth to occur. It is also 80 durability on the shore hardness scale. We've also looked at Flexio, which takes 10 minutes to harden, but uses resin that uses blue light. This requires the patient and the doctor to wear goggles when applying. The Cast 21 alternative is similar to Flexio, but takes 3 hours to fully harden and reaches about 150 degrees Fahrenheit when hardening using the chemical resin. This is dangerous to the user and requiring the user to wear a mold on their skin when applied.
After looking at the market competitors' strengths and weaknesses, our group decided on 4 main criteria. Safety. The cast must be safe to apply and non-toxic. This was our top criteria. Durability. The cast must be at or above 80D on the shore hardness scale, rigid enough to protect from the implications of daily life. Time of application. The cast must be applied and hardened in under 5 minutes. Breathability. The cast must have sufficient airflow to the skin at all times. As mentioned before, the Flexio cast uses a harmful blue light to harden, and it takes up to 10 minutes to cure. The fiberglass cast creates perfect conditions for bacterial growth, and it takes up to 30 minutes to apply and 2 hours to harden. Cast 21 lacks heat regulation during application and a quick application time. DecaCast meets all 4 of the requirements, as you will see. With the best way to meet our problem statement being a large amount of skin exposure, our original concepts had more breathability. However, they did not meet our durability criteria. Our current solution, DecaCast, has solved the strength issue while maintaining high breathability.
DecaCast is made up of 2 main layers, separately manufactured and conjoined together with an adhesive layer. Here you can see the 2 main layers coming together with pre-cut airflow holes. The living hinge is the foundation of DecaCast safe application. A living hinge is a thin hinge made out of the same material as the parts it connects to. It's the same kind that you would find in a clear fruit container that you would buy at the grocery store. There are 10 living hinges that fold around the patient's arms, and once each of the 10 gaps between them are closed, the cast is locked into place. The locking mechanism used to close and secure the cast around the arm is a simple pin insert design and male and female parts in an interference fit. This design allows for a fast and smooth application. The thumb component of DecaCast is comprised of 2 triangular plates, one on the front of the hand and one on the back of the hand. These plates restrict the wrist from moving, keeping the bone locked in place, making it able to heal. Embedded in the spines are cutouts designed to maximize airflow. 16 triangles are aligned and cut in the center of each spine. The cutouts remove 15% of the cast surface area, which decreases its weight.
Shown here is a spine of DecaCast made of the ideal materials and a full representation of the cast scope. We needed some way to test this cast breathability. Because bacteria doubles every 4 minutes, we had to make sure the environment between the skin and DecaCast replaces every 4 minutes. To do this, we compared DecaCast with the fiberglass cast. was an airflow test. The airflow test uses a wind tunnel to keep the environment a consistent environment. The wind speed was set at 10 miles per hour as a constant in the experiment. And since the results are percentages, the initial airspeed is irrelevant. After averaging the exit airspeed of DecaCast versus the fiberglass cast, the final analysis showed 122% increase airflow in DecaCast.
When selecting materials, we wanted to avoid traditional material hardening methods like our competitors. For the inner layer, we chose a silicone rubber, which is comfortable to the user and non-toxic. We also, for the outer layer, we chose HDPE plastic, which is durable and rigid when hardened. We will bind these layers together using cyanoacrylic glue, which will keep the layers together and bind in seconds.
DecaCast HDPE layer will use injection molding. The plastic is injected into a mold of DecaCast in less than 30 seconds per cavity. Injection molding can produce up to roughly 100,000 molds per machine life cycle.
For the silicone layer of DecaCast, we plan to use compression molding. This is a process where a material is heated to its melting point and then injected to the desired mold. Compression molding can produce a greater yield than injection molding and is efficient for silicone production, although it costs more labor-wise. The cost to make DecaCast came out to be $36.36. In the medical industry, a typical markup is about 80%. After applying an 80% markup to our device, the total cost came out to be $65.99.
For future design iterations, we plan to increase the size of the breathability cuts and reduce the thickness of the two layers, making DecaCast lighter while taking advantage of HDPE's full strength.
We plan on converting to overmolding, which is a process where the silicone rubber layer would first be injected into the mold, and then over that, the HDPE layer would be injected, bonding them together. This would result in the adhesive layer no longer being needed, which would dramatically reduce the cost of production. We plan on getting DecaCast approved, FDA approved as a Class 1 medical device, which would allow us to have our device covered by major insurance companies. The current iteration is designed with an age range of 11 to 15 years old in mind. However, moving forward, we would like to make DecaCast accessible to all ages.
We'd like to give a special thank you to Mr. Cahoon and our mentors. We also brought a material sample for questions.
Great job. My question has to do with the dynamic range of arms or calves. If this is a leg cast, people that work out, they may have more pronounced forearms like Popeye, small wrists, but the cast, instead of being cylindrical and very static in the inner diameter, how do you account for variability in the length of the arm or the leg or whatever is being protected by the cast?
Okay, so that our cast is designed to have it so we have multiple sizes that can fit multiple types of arms, and that's why the feature we want to expand to more than one age range, just so we can cover different sizes. That would account for the length, the different diameters between the wrist and forearm, and that's how we would do that for our sizes.
We designed the current iteration with the dimensions of a group member's arm in mind, but they're all easily scalable. So in the future, we hope to make set sizes so that you don't have to get your arm measured and then take like a week or two for the actual cast to be produced. It will already be ready in the size of it.
And then one follow-up question as far as your research into this problem space. Did you interview any physicians regarding what they take into account when they choose what type of cast material they use? for a certain reset or break?
So like the plaster casts that were used a while ago, they've obviously been used less. Fiberglass cast is cheapest and FDA approved. It's also not a splint. Many doctors will offer a splint if it's not a full break. We're talking one that's a full fracture break or after surgery. So we obviously, the fiberglass cast is one of the, obviously like the most common one on the market and FDA approved right now. Our competitors are not used as often. However, they have been FDA approved and are available.
And to more specifically answer your question, we did not interview any physicians directly.
Okay, thank you.
All right, my first question is about the application time. Why do you feel the need for it to be able to applicate and set in 5 minutes or less?
So the fiberglass cast, it can take a very long time, and we wanted to be able to have it be like a quick application process to allow it to be a quicker visit. And if you have a broken arm, you want to get it healed as quickly as possible. And you don't want to have as much time to risk another injury or even more.
Okay, and then I've had a couple of those casts in my life. The other one has to do with, so is it the silicone is what's against your skin, I guess, during this?
Yes.
So you want somebody to have silicone stuck to their arm for the next 2 to 4 weeks, easily? Do you see any issues with that?
We did not know that. I mean, there's we'll have a lot of moisture going in now, but it won't necessarily stick supposedly to your arm. There will be enough moisture to keep it, to have there be like a layer in between, so it's not always stuck to your arm, but it will also allow enough airflow through to keep that moisture out.
How does the cost compare to the other options that are out on the market right now?
So the standard fiberglass cast costs $240, and that's no insurance at all. That would be covered by most insurance companies. Cast 21 solution, we were unable to find a price for that. Their website didn't list one, and we reached out, and I didn't hear a response back from them on that. So we're assuming that it is covered by most insurance companies that advertised on their website. So ours, in future iterations, getting it FDA approved would allow ours to be covered by insurance companies, like major insurance companies. But right now, the $65 is significantly lower than standard treatment options currently.
And to add on to that, the majority of the cost is made up of the adhesive layer. And in the future, when we convert to our overmolding process, it will eliminate that and it will significantly reduce the price on top of the FDA approval, reducing the out-of-pocket cost to the consumers.
How heavy is it going to be? And is that comparable to the other casts? Because it seems like it's really dense.
Yeah, so one of our lower down criteria was going to be weight. It had to be under 2 pounds. Calculating from the spines that we were using, I don't think we took into consideration the adhesive, but from the spines, I believe it was around 2 pounds, or it was just under 2 pounds.
And that's comparable to the other?
Yeah, a fiberglass cast is normally somewhere between 3 and 2 pounds, so it's just under that.
Okay. Can you shower in it?
Yes, you can. It's designed, you can swim, shower, sweat, work out, because of all the airflow, it's designed to get your arm can be exposed to moisture and water.
And it'll dry?
Yes.
Yeah. Okay.
My question was, can you swim? Because that's what, I'm someone that had to have a cast actually removed because it had gotten wet. And so just water in general, showering is a common thing. I mean, it was horrible to try to have a leg cast and shower for 6 weeks. Also, please continue to take this further. This is the hinge technology you guys talked about. That was fascinating. And mobility is a big thing when you have an injury and how to keep things safe and healing at the same time. So definitely don't let go of this idea yet.
Thank you.
Thank you.
Summer in the Chesapeake Bay is always complemented by thousands of blue crab pots hanging off docks and boats. While we love this about the bay, what you often can't see is the impact these traps have on other marine life.
Good morning, everyone. My name is Hannah Burrell, and these are my partners, Delaney, Court, and Tammy. And we're proud to present Conserve-A-Turtle, a device aimed at protecting diamondback terrapins from being caught in blue crab pots.
In the Chesapeake Bay, blue crab pots are trapping diamondback terrapins ages 1 to 6 years old, as they are small enough to fit through the entrance, but too large to escape. Crab pots are usually checked once a day, so most terrapins caught end up drowning, as they can only last 4 hours without air.
Bycatch is the capture of non-target species. This affects many marine animals, including diamondback terrapins.
This is a map of the Chesapeake Bay. The areas in blue represent where crab pots are most often used. Now, overlaid in yellow and green are the areas where terrapins are most likely to be found. The overlap between these areas has resulted in the overall decline of the terrapin population, and today they're classified as vulnerable by the International Union for Conservation of Nature.
Found on every crab pot are holes called coal rings. They're required by law, and they are 2 5/16 inches in diameter, and they allow crabs not of the legal catch size to escape from the trap. Like these crabs, small terrapins can also escape. The problem lies in the terrapins that are small enough to enter but are too large to escape through these rings.
Some solutions already exist that target reducing bycatch. One such device is the crab pot chimney, which attaches to the top of pots and allows trapped terrapins to swim up to the surface to breathe until the pot is next checked. However, as this requires serious modification to the top of the crab pot, installation time is very high.
Then there's the 4 by 10 centimeter bycatch reduction device, or BRD. This device attaches to the entrance of crab pots, constricting them so that terrapins cannot pass through. However, larger crabs are also blocked. Lastly, there is the 4.5 by 12 centimeter BRD, which does not block larger crabs, but only protects 62% of terrapins.
Recreational crabbers are required by law to have a BRD on every entrance of every crab pot. However, commercial crabbers are not. Having to manage about 300 crab pots each and every day, and having to put a BRD on every entrance of every crab pot would be extremely time-consuming.
For our solution, we wanted the percentage of terrapins protected to be as high as possible, installation time to be under 60 seconds, and the final price to be under $2.50.
While brainstorming, we came up with a variety of ideas that ranged from some that would allow the terrapins to breathe while trapped until the trap is next checked, and others that would require modification to the trap, allowing them to escape.
But ultimately, we wanted to go with a device similar to a BRD that would prevent terrapins from ever entering in the first place. However, we wanted to stray away from the rectangular shape and instead creating one that would target the difference in shell shapes between the two animals. Terrapins enter pots forwards while crabs enter sideways. So we were able to overlay the front view of a terrapin with the side view of a blue crab and target the difference in these areas for our device. This is the first prototype of our device, Conserve-A-Turtle.
Many shapes were considered while making our prototype, some with millimeters to spare. However, none worked as well as the octagonal shape that enabled all crabs to move through while eliminating 95% of terrapins. This shape would also work if the crab trap were to land upside down due to its symmetrical shape.
In our testing, it quickly became apparent that no matter the shape, our device would have the same installation time as the regular rectangular BRD, which had an average of 78 seconds. In order to bring this down to our 60-second installation goal, we added an oval to the outside of our device. This allows our device to attach to the outside of the crab pot rather than inside the entrance. This brought the final installation time down to only 40 seconds.
Taking a closer look at the BRD on the left, it is apparent that it is not only extremely difficult, but very time-consuming to install. The oval on the Conserve-A-Turtle on the right allows the user to not only easily, but quickly install the device, saving time and therefore money.
Additionally, some BRDs actually reduce crab catch rates because of the sudden constriction of the entrance. To combat this, we created a funnel section of Conserve-A-Turtle, highlighted in yellow. This section allows crabs to gradually adjust to the changing space. Also, since they enter pots sideways, the triangular cutouts you see at the top and bottom of Conserve-A-Turtle allow them to crawl through easily.
Many materials were considered during our prototyping process. First was PLA plastic, which proved to easily dissolve under seawater and would melt under harsh UV conditions.
Though galvanized steel met all of our durability requirements, it was deemed too expensive for our project.
Lastly, we considered ABS plastic. ABS plastic was able to meet all of our criteria, making it our candidate material chosen.
Combining all these features, we were able to come up with our final prototype of Conserve-A-Turtle. In order for the user to attach the device, they'll insert the small section of the funnel into the entrance of the crab pot and use the 3 metal zip ties provided to secure.
Using our device, all terrapins are protected while crabs are still caught in the traps. As you can see, larger crabs that enter will be able to fit through Conserve-A-Turtle's shape and will not be able to fit out the coal ring, staying in the trap. Smaller terrapins can also fit through Conserve-A-Turtle's shape, entering the pot. However, they'll be able to escape through the coal rings, so they will not drown in the pots. Finally, larger terrapins that cannot fit through these coal rings will also not fit through Conserve-A-Turtle. They will never enter the pot in the first place, and they will not be at risk of drowning.
Currently, the regular 4.5 by 12 centimeter BRD costs $3.75. We wanted to bring this price down to $2.50, which we exceeded, with the final price being only $1.81.
This price is broken down into 3 sections: the ABS plastic injection mold estimate, the 50% retail markup, and the cost of the 3 metal zip ties provided.
Moving forward, we would like to further research the effect UV rays have on ABS plastic, along with protective coatings to minimize damage over time.
We would also like to gather experimental data during crab catch season, which is August through the end of September, to gather rates of crab catch and terrapin protection rather than the calculated values we have currently.
Furthermore, we would like to construct a legal plan to expand our market to commercial crabbers. We've already proven that we can make significant improvements over existing BRDs. The next step is to make them universal.
We'd like to give a huge thank you to the following people for helping us out this year.
Thank you, Mr. Cahoon, Willem Rosenberg, Andrew Keller, Mr. Hill, Juliana Wood, and Peter Threadgill.
I guess while you're organizing questions, we'll pass down the crab pod with our device attached to the front here. What? We are managing, along with one of the existing rectangular BRDs you guys look at. It's the 4.5 by 12 centimeter one.
So this would be a device you would only attach once, right?
Correct.
To each crab pot.
Yeah, one for each entrance, and then you're done.
Okay. Have you talked to the Chesapeake Bay Foundation at all about this device?
We have not yet.
This is another project I think you definitely should keep going on. I think you should get the patent on it. I think you should go to Chesapeake Bay Foundation. Yeah, like now, before you get the results for the fall, because I think we know what the results are gonna be. And just don't let it go, because you could save a lot of lives on this.
Thank you so much.
We have been in communication with the College of William and Mary, who is tackling pretty much the same problem. They have created multiple of the current solutions solved, but they have not had a success rate high enough yet.
Yeah, I was just gonna suggest, even if you don't, maybe if you started very small and you just had like 5 of these in a few traps, I mean, you can see results right away. This is a great idea, and they're always looking for ways to improve the marine life in the bay.
No, this is fascinating. I don't crab, but I know a lot of people around here do. Question is, how big of a problem is this, just for my own education? How many terrapins per year are caught in crab pots?
Yeah, so the exact number isn't known because nobody knows like the exact population of terrapins, but based on like the frequencies and like where, like the map we showed earlier, like where they're most likely to be, it is very significant. So I can't tell you exactly like how much because nobody knows, but it is known to be a very significant issue.
Okay. And then, I don't know if there's a way to judge this, but the intelligence of a terrapin versus the intelligence of a crab, because crab pots, lobster pots, they're pretty trivial. You know, you go in, it's nice and easy to get in. It's very difficult to get out. But if you kind of navigate that and figure it out, you can probably do a pretty good job of escaping. I'm just curious, are turtles more inclined to find the way out as opposed to crabs?
So the device basically works by constricting the entrance so that it's based on like their shape.
Yeah.
So based on like the interviews we did, it was one of our major challenges that crabs are generally smarter and more clever than terrapins. So they'll like maneuver through and be able to get out. So our device doesn't affect the trap's function. So crabs that enter will still be caught. So it doesn't affect how they would be able to escape. So only the smaller crabs that can fit through the cool rings would be able to get out. But everything else should remain the same.
If anything, it would make it harder for the crabs to get out because of the change in shape rather than having nothing on it at all.
Thank you.
And then my last one is just, does this restrict the amount of crabs that can fit into that hole? I guess like population-wise, are there crabs that are now too big for that, or did you not reduce that at all?
So what we did is I personally went out to multiple crab shops around us and measured the largest crabs they had. The largest crab ever caught was 11 inches in width, or in length, but that's very rare. The largest crabs sold are always over 7 inches, and the largest crab that I found at a shop was 7.5 inches. And yeah, 7.5 inches, that's what the shell said. And so that is the largest crab that is commonly caught, and you really won't see any crab larger than that. So we took the shell width of that, since they go in sideways, which is about 4 inches, and we made sure that was the overall width of our device.
Because we knew no one was going to buy something to put on their crab pot if it made them catch less crabs.
That was the main problem with the 4 by 10 centimeter.
Nice job, guys.